In the previous video in the series, we started looking at quantum computing using the concept of superposition. I would recommend watching that video first to get an idea of why quantum computing is so much more efficient and its differences and similarities compared to normal computers. The link to the playlist of all the videos in this series so far is in the card in the top right. In this video, we will look at another quantum phenomenon used in quantum computers, known as quantum entanglement, another vital element to help quantum computers gain such superior processing speeds. And we will look at some errors with quantum computers, which must be fixed before they can revolutionize the world. Now, to understand quantum entanglement better, imagine these two qubits in a quantum computer, recalling that each qubit could be in a superposition of 0 and 1, meaning it has some probability of being 0 and some probability of being 1 when measured. If these two qubits are entangled, it means that measuring one of the qubits immediately tells you what the output of the other qubit must be. For instance, imagine two entangled qubits, each in a superposition of half 0 and half 1, entangled in a manner which ensures that they are always opposite each other's values. Individually, if you measured one of the qubits, then it would just randomly give a result of 0 or 1. However, in this case, since the two qubits are entangled, measuring one of them as a 0 immediately means that the other qubit must be a 1, or measuring one of them as a 1 immediately means that the other qubit must be a 0. And no matter how far apart these qubits are separated within the computer, measuring one of them immediately forces the other qubit to take on a certain value. Their information is entangled since one of them determines the other. Because these qubits exist as random outputs of 0 and 1, quantum entanglement is essential for copying information and making sure interactions are carried out as desired. To explain why this is the case, I must first talk about one of the main problems with quantum computers, which can never really be solved as it is an innate property of the quantum computers. Recall that when a superposition is measured, it collapses to either a 1 or a 0 at random according to its probabilities. For instance, a qubit which is 80% 0 and 20% 1 could become either a 0 or 1 when it is measured, but as soon as it is measured, these probabilities are lost, since all one can see about the final qubit is that it is a 0 or it is a 1. And even if the qubits were 98% 0 and only 2% 1, when the qubit is measured, it could give an output of 1, and the fact that the probability of a 1 was so low is completely lost. Quantum entanglement can essentially create a copy of these qubits without needing to run the entire computation again, which saves time in processing and is key to making sure quantum computers can actually have an edge over normal computers. It also plays a key role in error correction, but before discussing that, we must discuss what exactly the errors are in quantum computers. Recall that the entire study of quantum physics relies on the tiny nature of the quantum particles, which make their exact behavior difficult to determine, allowing for all these strange concepts talked about through these video series to occur. As one could imagine, these qubits, which are simply quantum particles and superpositions, are extremely fragile to outside influence of even a singular air molecule, meaning that if a molecule of air were to hit one of these qubits as they were moving through the quantum computer, it could alter its state or even completely collapse the superposition, which would render it useless. It's not just air molecules. Any outside influence which causes too much change in energy of these qubits will negatively affect its state and make its carried information useless instead it has been manipulated from what it's supposed to be. This energy could even result from heat inside a quantum computer, since heat is simply how much particles are moving or vibrating around. Higher temperature means the particles are moving more, and lower temperature means the particles are moving around less. Theoretically, a state of 0 movement could be reached, which would be the lowest temperature possible since the particles are not moving at all. And this state where the particles are not moving at all is known as absolute 0. In order to preserve these delicate qubits, the quantum computer must be placed in a vacuum where there are close to 0 air molecules so that the qubits do not interact with any unwanted air molecules, which could change their state. And they also must be cooled to temperatures close to absolute 0, around negative 273 to negative 270 degrees Celsius, to ensure as little movement of the particles as possible so that no interruptions to the qubits occur. However, since these qubits are forced to move around and interact in order for the computations to occur in the first place, errors can't be completely avoided, and there is always a probability with every single interaction within the computer that errors can occur which make qubits lose their superposition form or can make their carried data inaccurate. However, without a way to detect these errors, they could go by unnoticed and cause the final results of a computation to be inaccurate and force the entire computational process to be repeated again, which wastes time. And this is where quantum entanglement comes into play to detect these errors. So let's imagine a qubit which is about to undergo some form of computation. Before the qubit is put through the computation, we can entangle it with another qubit, or multiple other qubits, so that the information is copied, and depending on what happens in the qubit during the computations, it will be reflected in the states of the other qubits since they are entangled. If any errors occur to the qubit during the computation, it can be checked with the entangled qubits to see if there is any difference in the state than it should be, thus catching the error and minimizing wasted time. Furthermore, one of the entangled qubits, which had already copied the qubit state, could be used in the computation instead, rather than needing to restart the entire process again. And at every single step, these qubits can be entangled to check for errors before and after computations, and if any errors are detected, one of the copied qubits can be used instead in the calculation, essentially allowing for the computation to pick up right back where it started without needing to restart. This copying of qubits to save what would be otherwise destroyed information due to the random nature of the superpositions, as well as the ability to detect errors, are key to allow quantum computers to have faster processing speed, and thus quantum entanglement is vital to the survival of these quantum computers. With these final two concepts of errors in quantum computers and quantum entanglement, we have finally covered all the basics of quantum computing. Hopefully, these videos have helped to teach you about why quantum computers are talked about so much. They aren't simply a method of speeding up computers as we know them today. They are an entirely new type of computation which revolves around the nature of the extremely small, with many counterintuitive phenomena which result from the uncertain nature of these particles. If you didn't quite grasp the quantum concepts explained through this video series, don't worry. Quantum physics is notoriously difficult to explain, and many scientists say that nobody truly understands quantum physics and why it really works the way that it does. But if you did manage to learn at least anything from these videos, then I applaud you on understanding something that much of the world is completely ignorant of. And I hope I have given you a new perspective moving forward.